machines, with a focus on the service computing. So let me just give you, maybe you already know, but just to be sure, I give you a very brief introduction of what a knowledge graph is. So a knowledge graph is a data structure, and people are widely using it. So how is this data structure defined? You have, so basically you can think about it like a direct labeled graph. So there are more complex definitions, but let's stick to this simple one for simplicity. So here we have nodes, and nodes are entities of the real world. Could be people, could be places, could be, I don't know, institutions. So this is a place, this is somebody, okay. And then we have labels that are relation names. So you could have relations such as is married to, or relations like was born in, okay. So all of those things. And the edges, what do edges represent? Edges represent facts, so instances of facts. So these edges in particular, source, arrow, target, represent the fact that Barack Obama in the real world is married to Michelle Obama. So we call it the head, we call it the tail, and this is not the... Okay, people always get confused between relation in terms of labels and relations like actual edges, but will be clear from the context, hopefully. Okay, so why people like those knowledge graphs? Well, it sounds like a very simple structure. So people like knowledge graph. They gained the popularity like approximately 10 years ago. I think that was the rise of research about knowledge graph. So if you remember, that was how Google search was implemented before 2012. You could ask how old is Harrison Ford, you got a set of links as an answer, okay? Then, things changed. And that's a screenshot from 2023, okay? So you are asking the same query and you get an actual answer with related linked information. You still get the links, but you also get more structure, And then things are moving further now, because there will be AI, large language models, and so on. But even the gap from this to this, was groundbreaking. And now what changed? They had this kind of knowledge graph, the massive knowledge graph, storing all the facts that they knew, at the time. So we have all the nodes here, all the edges, and Google search is not mapping strings to strings anymore, it's mapping strings to things represented as entities in the knowledge graph. So you can get, you can know what it is true more directly. Okay, so, great, Google search is great, but we're not implementing new search engines, are we? Okay, we're doing something different, but clearly we are, still we can get exciting applications of knowledge graphs to our context. So clearly, one easy way to use knowledge graph is not to use them as backbones of computing platforms. For instance, you can use, you can insert their application data, hardware data. So this is an example of a knowledge graph with a slightly different formalization. Here we have some application about the status of an application, the latency, the bandwidth, and also this is representing something, an application that is running on a platform, okay? And, but let me give you a concrete example, okay? Let me give a more concrete example. So, so this is some real-world example that we are working with in a EU project that we have called the Intent, okay? And the application data that we get are from a manufacturing company. So those people have manufacturing machines. So they use machines, and they have their application, they provide a platform that is a monitoring platform. So in this platform they collect and analyze sensor data and want to monitor and predict the health of machines. So say failures and delays and all of those things that manufacturing people care about. So they have the data that they have, okay? no, we transform them into a knowledge graph describing what are the applications and services in their platform. And we do that because that will enable reasoning about them. Not just searching, no, as we said in Google search, but really reasoning and interpreting what are the stakeholder needs. So let's go step by step. Here, for instance, no, the knowledge graph, we don't have Harrison Ford anymore. We have the name of a machine. This is a specific machine instance, so a machine that exists on Earth. And then you have the services here. Two services here that are, I'm very sorry. Okay, two services here that are that are supported, but that can be executed regarding this machine state and product data, two services. Okay, and then they have also some other containers that are required in order to make things running correctly. Okay, so what is the application that we figured out? So we're not talking about search anymore, really we're talking about reasoning, and more specifically, really understanding natural language requests. Okay, so suppose that there is the maintenance engineer here, okay, that wants to know the status of a certain machine. So they need an application. Okay, so of course they could, with technical background, they could do the Docker command, they can log into the computing platform and do the operations themselves. That's of course an option, and that's how they are governing things today. But not in the future, what is the aim? That somebody without the technical background can still operate their platform. So how do we enable somebody without a technical background to operate, or even somebody with a technical background but wanting more efficiency and user-friendly? And the way is that we can enable natural language queries. So natural language queries are popular for databases, are popular for search. Here we are using natural language queries to describe computational intents. Okay, so they are not asking for the age of Harrison Ford, they are asking, I want to know the status of a certain machine. So we have several components here, okay, and thanks to the facts that are stored here, we can translate, this natural language intent into a machine specified language. A language that can be run automatically by a system. That's the bridge. So instead of writing this, you can do that, and then the system will take care of it for you. Okay. So of course that requires to understand what are the services described in the natural language querying. So they have to be mapped to the knowledge graph. And then once they are mapped to the knowledge graph, and for instance, that this machine can use this service, then you can get the containers that are needed, and do the deployment operations. Okay. And for them it's very time saving, both because they can directly involve the stakeholders that are non-technical people, both because people that are technical, of course, they can, we also technical like to not write code sometimes, That's something that we all like, okay? Then maybe we read and correct, but things can be, you can speed up things. So here, that's a very preliminary results. We had 10 intents written by experts. Intents where all the intents had a related container list as a solution, ground truth. Okay, so we represented the problem as container prediction, okay? And now we have always the right list of containers that is identified with this method. Okay, of course that's the intents is not like a benchmark of intents, but that's something that is going on. Okay, so that's the application that we have in mind. Okay, so everything works because the graph has all you need. You might say, okay, so that's the assumption, but the assumption might not be true. Okay, so here we have a very manually curated example where you have all the facts, where you have all the things, and I showed you very exciting things that you can do if you have the facts. But you rarely have, because typically what you have is a subset of the true fact. Why? Because data are handled incorrectly. So downloading procedures, extracting procedures, parsing procedures may fail. And so you might just skip edges. Or there can be intrinsic observation issues, so that you cannot measure that fact at some point. So for that reason, okay, the true assumption that we want to somehow tackle today is having all the facts, assuming that you don't have from the real world. So you really need to predict what is missing. So that's really the focus of the AI techniques that I will show. So for instance, example about service availability are great, but sometimes might be a little bit difficult too, so we will alternate. We'll do some Barack Obama, some services examples, depending on the topic. Okay, so we go back to Barack Obama for a moment, but remember that can be, of course, application data. Okay, so here, what we have here, so we suppose we have a toy knowledge graph, where I have Barack Obama born in Honolulu, that it is in the United States, and the edge that we are missing is nationality. So we don't know from the real world, but we might infer from the data that we have. So we don't have all the data directly, but we want to infer what it is missing, so that at some point we have all we need, and we can run things. Okay, so that problem, it's a traditional problem, and it's called the link prediction. Okay, so why link prediction and not just fact prediction? Whatever. I mean, there are you can call it however you want. The point is really predicting facts. Okay, so the link here, so you can have it in many flavors. The flavor, so you can predict missing entities, you can predict missing labels. So you can have it in many flavors. The way that we are discussing it, it's really inferring the edge. So entities are all there. We're assuming in the data missingness model that facts that are missing are edges. Okay, so that's a simplification that we do. So what do we do now? Okay, we do introduction to some methods for this problem. Then we describe what's missing, what are the challenges and possible research directions. Then we describe very quickly a very technical challenge that is how to explain. When I do AI, I always want to explain it. I don't want it to be just accurate. I want it to be truthful also. Okay, and then we do concluded remarks. Okay. So regarding methods for link predictions, so people think to AI in very different ways, okay? And there are broad families. I've met people that do this problem in very different approaches. For instance, there are rule-based methods that are symbolic approaches and can be great, can be really great, and I like them because they are interpretable. Unfortunately, the performances are sub-state of the art for now, and so we'll discuss embedding-based methods that are neural methods. So of course, in the future, people are developing, and also right now, people are developing neuro-symbolic approaches, mixing the strengths of both methods, but for now, for this tutorial, we will focus on embeddings. Okay, so we'll embed things. Okay, great. Okay, so how do we do this? Okay, so we wanted, as I said, we want to predict missing facts. But you don't just go to the knowledge graph and say, okay, what's missing there? You have to do some structured routine. So the structured routine that people do is doing missingness queries. Okay, so the missing sense queries, and you can iterate on those. That's very time expensive, but that's how things are carried out right now. So you just don't ask AI methods what's missing. You ask what is the nationality of Barack Obama, or what is the spouse of Michelle Obama, no? Where is located Jakarta, and wherever you have. So you have to know what is the fact that you want to predict. It's not coming from the box. You have to know what is the fact, and that's a limitation, of course. You have to know what is the fact that you want to predict, and you ask it. For instance, here you ask Barack Obama nationality question mark. Okay, and no available facts are used for computing plausibility. So you will get a ranking of plausible answers, and the top one is the best candidate. For instance, those are places, those are the places, and maybe you will get USA ranked before Indonesia, meaning that that's the candidate answer. Okay, so technically this is how it is done. You ask a query, you get a ranking, and you examine the top of the ranking. Okay, and with that you can complete the fact. Okay, so remember, if we had machine data, you would ask machine data has service machine state question mark, has service question mark, and maybe you can get machine state before product data. Okay, and that's the service. Of course, you can have multiple answers, and those can be, for instance, in this case you have both, and you can have in the ranking even multiple answers. Okay, and you see, if for some reason your service inspection routine failed to detect this one, you can predict from available ones. How? For instance, because you have other things in common, and you can say, okay, so this service is missing. Okay, so that's the interface in a sense. That's how you operate. The internals are wide. I mean, really, I'm still wondering how it is possible that this machinery works. But it does, and of course it makes sense to focus on how is it possible. So people have devised a huge set of embedding techniques with all the shapes, torus, spheres, I don't know, whatever you come into your mind, they tested it. Okay, and there are indeed properties of the spaces that enable more accuracy of prediction. Okay, so the embedding will be, we will map entities and edges to a latent space. And the latent space will enable us to rank. So that will be a ranking problem, basically. From now on, we forget everything, ranking. The problem is ranking. Okay? And ranking with embedding. Meaning that we have to solve a ranking problem over vectors. So now, from the beginning, that's how the thing is really implemented, technically. So we have vectors, so every entity or label or fact is mapped to a vector. And then you need to use those vectors to compute the value of a plausibility function. So you have a function phi that is defined over vectors. You want it to be high for facts that are true. How? Well, that depends on the model. I think the first model that was devised in this setting, it was a purely transactional model. So now, for instance, you have the vector of the head, the vector of the tail, so this is Barack Obama. So this is nationality. and this is USA. So you want your vectors to be to have a value such that all those relations holds for true facts. Indeed, this is supervised. So you have now you do the split. So you have the knowledge graph. You split it into training and test. Okay. You minimize a loss for those relations for the facts that you have in the training. Okay. So you get the actual vector numbers. And then now you try, for instance, negative log likelihood, whatever, and then you ask. Okay. So here, for instance, if you want to know the nationality, you don't have this vector. Okay. So you don't have. So you have this is Barack Obama. This is nationality. This is USA. So you don't have this factor. You ask Barack Obama nationality question mark. And this is USA because that's the closest one. Indonesia maybe doesn't do the trick. Okay, so Indonesia is there, but really doesn't do doesn't verify the relation. So what is the relation? Well, it depends. Let me show you one simple slide. Okay. So there have been two big families of models. Okay. So let's do pre-large language models and post-language models. Large language models, as in all the domains, changed how people do things. Okay. So before going to that, let me show you why we say that those approaches work. What does it mean that this works? Okay. So when we do the training, and minimize, for instance, the plausibility function, we will have a loss. Like the log likelihood for understanding whether our vectors are satisfying. Okay, means that they approximate the truth, the training fact. Okay, we need to do the testing. How do we do the testing? So the testing is that we take the facts that are not in the training, and then for each of fact we put away, we remove the tail, put a question mark, ask the system, and measure one thing. So the thing that we measure is whether the true answer is in the top K. So that matrix is called hits at K. And people are using it throughout the entire literature. There are other metrics, but probably the most popular one is the hits at K, that is a traditional ranking metric. So if the vector that is closest to this is indeed USA, you are happy. You are also happy if the USA vector is in the top K. Okay. And K, of course, can be 5, 10, those are typical values of the K. Okay. Okay, so as I said, methods distinguish because they use different scoring functions. Okay, so not the triangle. The triangle is one of the earliest. There are much more complex functions out there. And the loss function that they have. So really, you need to choose the scoring function and the loss function, and things will be very different. As I said, there is the split when large language models were released. So there is a big family of methods. Here you have for the slides. Now they're using matrix factorization, geometric. This is the triangle one that I showed you. Okay, but then there are others. Okay, deep learning methods. So they have different properties. And then some point. Large language models came out of existence. So at this point, people are trying to use large language models to solve the link prediction problem with mixed results. So this is a place where you don't have like large language models completely rewriting the entire state of the art. No, that didn't happen yet, okay? But let me show you what is the main idea. So there are many ideas. One of the ideas is doing the in-context learning, and then I'll tell you why it is not that immediate to use large language models to do that, and why it applies to service-oriented computing. Okay. So how do they do, people? So they do in-context learning. Context learning means that, so that's a figure that is from a paper, but the point is that they do they describe the model in the prompt. So they say, Barack Obama lived in Jakarta. Also, Jakarta is located in Indonesia. Barack Obama has spouse. They describe the knowledge graph in the prompt. After describing the knowledge graph in the prompt, or shall I say the relevance, the portion of the knowledge fact that it is, of course you cannot describe the entire knowledge graph because it will be out of the context, and the knowledge graph is massive. So you cannot just put the knowledge graph inside a prompt, okay? No? So you can retrieve the portion of the knowledge graph that is most relevant to a query. You describe to the prompt, and then ask for ranking. What is the answer that you feel most true? USA, Indonesia, blah, blah, blah. Or just rank the entities, not by plausibility. You can get good results, but here is a catch. That works mostly for common sense knowledge graph. So that's something that people forget all the time. They treat data, now also I come from the database community, they treat large language model can handle data, but what data? Data about common sense? Of course. They don't need a knowledge graph to know that the nationality of Barack Obama is USA. They don't even need the in-context learning. They can do zero. Because they know from the data space. Point is, if you give them machine data, that cannot do anything. So if you try to solve those problems on sensor data, application data, all those things, they just cannot work because there is no common sense. So that's one big limitation. Of course, lots of the benchmarks out there are about common knowledge, which skews a lot the performances of large language models, okay? And also, there is another technical limitation, but that's maybe less important, that the size of the facts that you can give them is limited by the context, no? So if if you need many facts for doing an inference, then that will be supported. But so the point is that the biggest limitation is that they work mostly for common sense. But clearly they are another tool that we have, another arrow that we have in our. It's another tool that we have. So I mean, I'm not saying not use them, of course. But maybe potential novel works are more in the space of hybrid methods, no? So there will be an embedding part and a more conversational part, as well as a symbolic part that we are not discussing in this tutorial. Okay, so questions before moving to the next. So we will have time at the end anyway. Okay, so everything is great. No? So then what are the strings attached to those methods? So what are the research directions that people are pursuing right now? Well, the biggest limitation that those methods have is reproducibility. So if you try to just get one of those embedding methods and try to train it and run it on your own, you will face significant challenges. Okay. Unfortunately, there are not. My postdoc is not here with me. Otherwise, you would feel it from his face. When thinking about reproducing that stuff, it's a nightmare. Why is that? Because they're very sensitive on hyperparameter setting, and they have lots of hyperparameters. Okay, so if you and papers report high performances for very specific configurations of their hyperparameters. So there is a huge ongoing effort in literature to standardize libraries. And to be, that's very good actually, this one is very good. Okay, and to standardize methods and provide configuration files that are certified giving those performances. So for instance, from this library you can download both the code of models and the configuration files that can be used to get the highest performances. On some datasets, if you have your own data, well, you will need to find the hyperparameter configuration on your own. That makes it even harder to reproduce their impressive results. Some of those have something like 90% of hits, 90, 95, meaning that they can technically anything, so they are very promising. But still, there is a significant gap between the results shown in the paper and the things that you can get in a more application-oriented environment. Okay, so contributing to this scene is very valuable. Okay. Another problem is benchmarks. So as I said, all the methods are tested on common sense knowledge graphs. That's a major limitation per se, because that doesn't represent the overall set of data that we want to use, of course. Okay, but still, even if we wanted only common sense, they have still problems. What problems they have? So one of the problems is what it is called a data leakage. Okay, so for instance, there are lots of relations that are trivially true. Okay, for instance, if I have in training Europe has part Republic of Estonia, then in test I have the inverse question. Estonia is part of who? Then it's very easy to answer. And of course, embedding-based methods are very clever. They try to optimize something. So if you have an easy way to do that, to score a high result, they will. So if you, like a student, if you give you the easy questions, they'll try to score them first. They will not focus on the long tail, of course. What's the point? They will focus on a big portion of easy questions and get very high results. You don't know it, but that's what they will do. So the way is removing those trivial questions. For instance, duplicate relations, football player, current team, sports team, position. So those are all relations that really describe the same thing. Or transitivity. I'm friend of X, X is friend of Y, am I friends of Y? So all those things are very easy to predict, and sometimes they can represent the majority, and so you can get very high hits at K for those things, and you don't want that to happen. Okay, you don't want it to happen, so now you need to identify them, manually remove them, and there are efforts for doing that. So those are references that you can use. So there are efforts of doing that, of re-evaluating things more fairly, and but something that is missing completely from the literature is non-common sense knowledge graphs, like this one. That really have to process. You cannot use background knowledge for doing those kind of inference. Okay. So those benchmarks are completely missing today, and that will be a great addition to the literature, in my opinion. Another challenge here. Let me show. Another challenge is not the hits at K metric. So the hits at K, the way we say, oh, this method is great, is based on the hits at K. The hits at K is a traditional ranking metric that comes from information retrieval, okay? And it's for search. Like for Google search, no? If the website that you want is in the top K, you're happy. So that's really the same metric, okay? But here things are slightly different because we're not doing the search. We are doing some different task, and now search-based metrics can do bias. Why? Oh, suppose I have 3 models, and you tell me which one you like it best. So model A uses, I don't know, very simple latent space. Model B uses a very complex torus whatever shape latent space. Model C is rule-based. Plain symbolic approach, like, I don't know, inferring rules from their frequency. And you tell me which one is best. So I'm predicting which is the nationality of Tom. Model A will give me the ranking Canada, USA, Toronto. Model B gives me Canada, USA, Toronto, same. Model C gives me USA, Toronto, Tom, Canada. Of course, this is rule-based, now we like deep learning, so rule-based is failing. Okay, because that's outside the threshold, the K, that this figure is 3. Okay, but if you would say that those two are better than this one, okay. However, this one is very different from this one, because even if they both rank Canada first, here the score is 8 and here the score is 1.5. Meaning that this one is a tiny hyperparameter variation away from returning something completely not useful. Whereas this one is more robust, because it's giving Canada a very high score, it's more confident. And confidence-based metrics do not exist today, which maybe could be a great addition to the literature in the next few years. Okay, and there are of course probabilistic frameworks that can be used. I come from a statistics department, I'm a computer engineer, but come from a statistics department, and they have nice theories that can be applied for measuring in a more robust way performances of link prediction systems. And of course, no, to conclude this part, as all the AI systems on Earth, they are affected by bias, of course. So how do we measure bias here? So forgive me for the very dense slide, just look at the table. So how do they measure bias? So bias here is very subtle. So there are, if you look at the topology of those knowledge graphs, that are answers that are, so this is not leakage, so this is completely different from leakage. So there are answers that are something like default answers. What is a default answer? An answer that is typically very true. For instance, I have a data set with majority of people speaking English. Few of them speak Italian, few of them speak Greek, and only one speaks French. Okay? And I ask the large language, the knowledge graph embedding method, what is the language of Donatella? Of course you try English, no? I mean, maybe it's false, but 90% of the time it's true. So those default answers can be much more subtle to find than traditional leakage, because that's not leakage, that's really biased in the evaluation data set. And that can, if you remove the biased methods, so this is the drop in the H1 metric that you can find. Something like, so this one, half, 15%, 50% of drop in H1 by removing default answers. Meaning that it's just guessing, it's just clever guessing, not really understanding the data. And there are other biases that are variations of this default answer system that can be studied, but that's really the point. And of course, building non-biased datasets, and also here using datasets like sensor or service or application data. No? Bias is in human-made database. If you use application data, bias there will be much less. and those of course consequences are huge drops in H1. Okay, so what is the conclusion before we go to the last part that will be very short? Hopefully I should have time a little bit. Okay. Even accurate, lot of literature case about accuracy, scoring high hits. But even accurate predictions, if made for the wrong reasons, can be harmful. Okay, so let's forget about accuracy entirely, and let's focus on whether we can identify the reason of a prediction. And maybe in the future we answer whether LLM-based methods are more or less prone to bias. Okay, I will give you a very quick glimpse on what is explainable AI on this matter. Who's familiar with explainable AI? I think few of you could, okay? So explainable AI is something that was created in 2018 probably, okay? So that's about dogs. So people were using a classification, wolves versus huskies. So they look remarkably similar, It's hard even for humans. But this classification was skyrocketing accuracy performances, getting 98 accuracy, whatever, very, like this one is a wolf, this one is a wolf, this one, so this husky, I mean, it's not that different from this wolf, I mean, the color maybe. So they were asking, okay, what are the features that are used? So the experiment was nice. So they were covering random part of the picture and asking the prediction again. At some point it will fail, of course, because if I cover the face, the tail, the pose, whatever. So they were saying, let's see what is the portion of the image that this method is really needing. And the portion was the snow. The portion was actually outside the animal. Well,
snow.
Snow, exactly. That's accurate predictions for the wrong reasons, right? So it was using the background snow. Relating to it was very good at detecting a huge bias in the dataset, where all the wolves were in the snow, whereas huskies were on the forest. Okay, so it was really classifying based on the background. Very clever. So let's really worry about this and build a new research field for those things not happen ever again. So the explainable AI field was born. So for link prediction, we can do something very similar. So we cannot cover, of course, we cannot cover portions of the figure, but we can cut edges to see which edges are using. Okay, so we cannot cover the figure, but we maybe can cover some edges. Okay, if I remove the fact that Barack Obama is born on Hulu, what's your answer? What's the nationality? If he's still saying, no, United States, well, he's not using this one. If it is changing its mind, then that was the edge that was really meaningful for that prediction. So we don't want the snow, we want something that is truly related to the answer, okay? Of course, that is, and of course, for instance, in the service data, here remember, our machine knowledge graph, if I remove this container, can you still say what is the service that I'm using? Can you still predict that? Also, that's very nice, but also very problematic to do in practice, because it's very difficult to do the retraining, okay? It's very difficult to do the retraining, If I want to build an explanation, I cannot just remove edge, retrain, remove edge, retrain, remove edge, and retrain, because that will be very expensive. It's hundreds of hours of GPUs. So we cannot really do the same, do what they did with the image classifier. that won't scale in this setting. So this is our paper. We did something very simple. We are cloning edges, we are cloning nodes, removing edges from the cloned nodes. Here, this is the original node. We clone it. We attach all the edges. We remove edges that are candidate explanations, and we do the fine-tuning, not the entire retraining, only the fine-tuning on the node. If the clone deviates from the original one, then the edge is considered important. Of course, there are some technicals on how to choose clones, how to choose edges to remove, how to do the fine-tuning that are covered in the paper, but that's the very key intuition and can give state-of-the-art performances. Limitations here, because things need to progress, okay? That's local explanations. You won't see an edge that it is far away from the node if it is used by the system. So that's a limitation that all explanation models have currently. Hopefully in the future we will build better techniques that take into account things like that are more farther away from the original node, and detect more subtle features in the system. Okay, conclusions. Okay. Okay, so we discussed some knowledge graph completion methods applying to some emerging applications, and then there are many open directions that we tried to cover. For instance, how to incorporate the systems into actual computing platforms, building better benchmarks that don't have the limitations that we discussed, and evaluating how LLM can do in this application, whether they are more or less prone to bias in no common knowledge setup, and that we need novel and better explanation methods to capture global patterns that are so important for assessing the trustworthiness of a system. Okay, so I'm done here, so I thank you for your attention, and let's see how many time we have.
Questions?
So thank you. I was curious. So in the beginning you showed this picture in which the knowledge graph was between the query and the LLM, if you wish. And you made this experiment. So I was wondering what happens if you remove the knowledge graph and go back to the natural language. Have you benchmarked the results? So at some point you said it works only for common sense knowledge.
You mean this one, This one. I understood this one. Ecco, this one.
Yeah, okay.
You say you remove the knowledge graph and you benchmark that.
Yeah, no, but you also had an experiment in which you tried yourself.
This one, the bias.
No, not before. But I wondered, did you experiment with removing the knowledge graph? Yeah, this one.
This one, okay, this is
okay. And see if you get anything close by. Because I wonder how much is over. If you take the knowledge graph, you go into embedding and then you use it. Exactly. And the LLM already has its own embedding. So what is the added value of those two levels of embedding? Does anybody experimentally show that you really have an advantage with that?
Oh, that's a great question, actually. Okay, that's an excellent question because that's exactly the point. So here we are asking queries about a proprietary database. So there's no way an LLM can tell you. Because of the size. So you could do that, for instance. So you could do the description. So you could do something hybrid, of course, as you said. So you could do here, you say you remove the knowledge graph. Okay. So in the prompt, you have to describe the context somehow. Okay. So how? You mean you could do in-context learning?
Add a RAG and then give this information.
The RAG, you say, here? I mean, the RAG, and we do have a RAG component here, okay, can do this step. So can understand which are the nodes that are relevant, but cannot do the translation directly.
You have experimental data on this, that was my question.
No, we don't have experimental data, of course. No, we don't have experimental data on that. But technically, I mean, it's the last step that is missing. But yeah, we do have already some RAG system inside. Okay, but yeah, no, that is a great point. I mean, we should really, I mean, this is preliminary, but for full, you should have baselines here that we don't have currently. You're right, exactly. So technically, what I'm saying intuitively, okay, here, this, so you need, so this is based on, let's say, a specific language. So the overall goal is to support even more less strictly specified languages, so you really need something that is parsing at the end, so some expanded functionality, okay, with respect to a basic, let's say, retrieval task. But right, so we could do the following. We could simplify this task more, and then run a basic retrieval pipeline, and so that is something that will be a very nice addition. Thank you.
Other questions? If no, I have a comment like similar to Marco. When we build the data, basically we assume that the data is modeled, because building a knowledge graph means that you have created a model of the data. In the end, it's, let's say, even if with different properties, you are creating the database, a structured database. So if you have a structured database, I think that in the most of cases, except the web search that you presented as origins, you have the knowledge of your data. So I can apply the deterministic method for doing reasoning, for doing whatever I need. So we do all the stuff on the embedding when we have probably so huge quantity of data that we assume that the model was built not in a curated way. Is there evidence of this? So what I'm curious is that when really we need these embedding techniques because we cannot solve in other approaches. You get what I mean? If I have 2 million of edges, I understand that probably no one has modeled end by end that Obama was born in certain place. But so I see some applications, but I want to know your opinion, because you work on this. Because if I have to do for traditional data, for example, a record of a citizen in a country that are some millions, and typically they are very curated, I don't see the advantage of doing the bending. So for me, at the end, is a database. So I don't know if it's a philosophical question.
No, thank you, Massimo, because that really relates to the foundation motivation of why we do that. Okay, so I was looking for a slide that unfortunately it is not in this deck. Okay, so people tried it. Let me show you. So there are two things here. Okay, so there are two things here. Let me show you. Maybe this one.
It was just in the meanwhile that you search for the other. Understand if we have the knowledge graph of the web, of course it has been built automatically, so huge a quantity of data that I understand why you need to have statistical approaches. But if I have to deal with my service, my database, or whatever, why I need this?
So you have two reasons, okay? So the fundamental, so let me give you an answer in two parts. So the fundamental reason is that from a database perspective, data is never 100% correct.
No, but there are deterministic techniques to correct it. You don't need the embedding of the
Okay.
of data quality research
that with other techniques solve it. So if I am in the order of millions of tuples, I have statistical,
Sure.
edit distance, many other techniques.
Sure.
You don't need to do all this machining.
And there are indeed, for instance, okay, I found the slides, so you can see that there are the references here, okay? So there are two families of approaches, the embedding ones and the rule-based. Those are based on frequency of things. So they are deterministic. So you have statistical methods. So there are very nice methods. For instance, those two, one is EMI and the other is ENI, Bohr. They are used. It's not as though they are bad. They are used because sometimes they're enough. And of course they're interpretable. So of course if you can use those methods, go ahead. That is even better because they're interpretable. Okay?
We have the coffee break, but my question is more, I just leave and then we discuss. My question is on how do you build the knowledge graph? So it's assumed that the knowledge graph is built always by a human, or is assumed that the knowledge graph is built automatically?
Built automatically.
But then why do you solve the issue of incorrect data after the knowledge graph with embedding and not solving a priori by investigating better techniques to build the knowledge graph? I want just to know the state of the art.
Of course they are complementary, and there's a huge research on data extraction. Of course, as long as you know, you can do both things. So, but there are things that are inherently inextractable. Okay? So of course you can do that, but things that are inherently extractable because you just don't have the piece of information in the documents,
Okay.
then you have the inference part.
Okay. Okay. So thank you again.
How do you eliminate duplicates when you have a knowledge graph?
Oh, nice. So there is duplicates are up.
I mean, duplicates as in there are two nodes that have similar meaning,
Yes.
right? And then you find a way to assign those. But in knowledge graphs, you have 3, 4, 5, 100 topics.
Of course.
You have almost duplicates.
Almost duplicate, and you do have. Indeed, there are methods that are called. So not record linkage is entity linkage. Okay. So entity linkage are methods that do duplicate detections of graphs. So typically those things work in pipelines. So you never have something solving all. You will have improving extraction, as Massimo said, no? So you have something to improve extraction, something to remove duplicates, and then that is going to it's meant to be as a downstream task. After you did everything you could on the data themselves, improve the extraction, remove the duplicates, and doing all the data cleaning things. At the end, you have a database that is no good quality, but still missing things from the real world, and then you do the embeddings. But there is a huge literature on entity linkage as well, that is removing duplicates from knowledge graphs.
Is there anything new you're doing in the sense that you use maybe the next version of LLMs to do the
No, for linking nodes in knowledge graphs, I did the most work on removing duplicates from tables. I actually don't have personal works on removing duplicates from knowledge graphs. From tables, lots. And LLMs, of course, are a huge part of it because they are great to measuring similarity of pairs. But they are very bad at prioritizing what is the portion of the data that you have that is most dirty. So they can be used in those pipelines as well.
I'm out because I need to maintain the session. So
We have 10 minutes for the coffee break, and we'll start at 11:15. Unfortunately, because we have the exclusion, so
it's an hard constraint.
Yes.
Yeah, out of case and here, so we did stuff really fast. Yeah, it was a and some part gets sold too much. Yeah, you are. This is what yeah, they gave them 3 years. Yeah.